Pareto frontier, with which, of course, economists are very familiar. It is an effective and transparent way of summarizing trade-offs for economists. We often use them for two goods, clothing and knowledge, or leisure and income. But here I'm showing it for two bads. On the horizontal axis, we have deaths. On the vertical axis, we have output loss from mitigation policies or from the pandemic itself. So the best place you would like to be is zero. That's there are no excess deaths from the pandemic, and you don't lose any output. But of course, that's not going to be achievable. The black line here is what you can achieve if you limit yourself to uniform policies, meaning that the same lockdown, the same mitigation, the same other policies are applied to all individuals in society. It is convex to the origin. That's how it turns out in general. And then I've also indicated 2 points of specific interest. One is maximal feasible control. If you say, we're not going to allow even one excess death that we can prevent, that would be the most severe lockdown that you can imagine, subject to, for example, medical services being provided, etc. So we're going to allow for some essential workers, but subject to that, this is this black point here. The other one is this no control point, which is what essentially Donald Trump and Jair Bolsonaro would have liked, which is no control, not even much social distancing. And that, of course, maximizes deaths because it maximizes the spread of the infection. But this frontier already highlights that it's not particularly good for output loss, because when there is so much disruption, that will have economic cost, in particular because of lives lost, productive lives lost, and other things. Now, the main conclusion of the paper is that when you allow for targeted policies, this curve shifts down like this. So the no control and the maximum feasible control points don't shift down, but the rest of the curve shifts down like this. So you can achieve much better outcomes, especially in the middle, when you have when you are exploiting the trade-off between output loss and death. What these targeted policies take the form of is very important. But what I'm going to show is that most of the gains, almost 99.9% of the gains, can be achieved by what we call semi-targeted policies. Just apply a protective custody form lockdown on the over 65s, which are the most vulnerable group. That does not then again go for some of the claims that were made that you can let the young or school children immediately go to do whatever they want, because there is no perfect lockdown. So if the disease virus spreads in the population, it will go to the 65 group. So you do apply a pretty strict lockdown for the young as well, but a differential one in a way that I'm going to show you. And its logic and its purpose is different, as I'm going to explain. And then testing is important. Of course, some caveats. We are not epidemiologists. That's important. So that's why our contribution is not to the epidemiology aspect, but to the conceptual, methodological, and policy aspects. It has to be said that model specification and parameters are very uncertain. This is something that both epidemiology and economics contributions suffer from. And sometimes people are insufficiently clear on this. We know so little about this virus, even 8 months into its spread. And as a result, optimum can be sensitive to parameters. I want to say that upfront. But actually, we're going to see that the gap between the optimum that is uniform, an optimum that is targeted is very robust. And I'll try to explain, I'll try to give an intuition for that. All right, the rest of the talk, I'll talk about the model, calibration, main results, and very quickly about robustness. I'll just highlight one or two things. Here is the SIR model. I'm going to start from the baseline equation of the SIR model, which is this top one. It's essentially an exponential growth type equation. Infections come from contact and transmission between susceptible people, who are either everybody or mostly for these viruses, and as has been hypothesized for COVID-19, though not proven, those who haven't become infected in the past, or if there is a loss of immunity after infection, they have not lost their immunity yet. When those susceptible S come into contact with I, the infected, at some rate beta, that generates new infections. Beta, in general, I'll come back to this, is a mixture of two parameters. How likely are they to be in contact, and what's the likelihood of transmission conditional on contact? Now, the standard SIR model takes this equation and can be summarized with this upper picture here. You have the susceptible become infected. Now, this is a little bit COVID specific, but it's a very trivial extension of the standard SIR model. Once they become infected, there might be differences in the severity of their infection. This is relevant for the age groups. So we call that ICU and non-ICU. Some may need an ICU, intensive care unit treatment, the rest don't. And then they either recover, or those who need intensive care unit may recover or die. That's the standard SIR model. Now, what we're doing is adding multiple groups. So this dynamics goes on. And the interesting part is what this shown is here is in red, the network contacts. So the people in group 1 can get infected by the infected from group 2 and so on. And throughout, I'm going to use the notation from standard SIR models: S for susceptible, I for infected, R for recovered. The key equation, instead of this top one for our paper, is going to be this. New infections in group J is going to be beta times the susceptible in group J. IK infected in group K. Rho JK is going to represent these red network contacts. So you sum over rho JK times IK over K. So you get this infection from other groups. Namely, we have J groups. I'm going to denote the rate at which an infected becomes in need of an ICU by iota J. 1 minus iota J is a mild case. Most young people seem to have it mild. But comorbidities matter as well. That's something I'm going to say at the end, but let me mention it again here. Comorbidities are very important, things like diabetes, asthma, and other chronic health conditions, as well as a history of lack of proper care, may make your needs for ICU and death rate higher, just like the older group. But I'm not going to get into that because that introduces some other implementation challenges. All infections resolve at some rate gamma J. All mild recover, as I showed you in this picture, but the ICU may have time varying death and recovery rates. Time varying because this will depend on whether their ICU needs are met, whether they get ventilators and intensive care unit treatment. So in particular, we're going to model that by assuming that the death rate is increasing with a function psi j in the total infections or total need for ICU needs. We're also going to introduce testing and isolating. There's a flow rate tau j at which non-ICU people are caught and as having the infection and forced or convinced to isolate. That's different for ICU people, because once you go to ICU, you're going to be isolated from the rest, but you may still pass it to other ICU patients, so that needs to be taken into account. So combining these with the ICU needs, etc., you get a combined coefficient eta j, which is what is the probability that a typical infection is not isolated. And then once you recover, you may or may not be recognized as recovered, and that may or may not allow you to go back to work more freely. And then we look at various different scenarios there, but it's not important. The more important part is the economic modeling, and I'm going to keep that simple. We're going to assume that there is an L bar J maximum on group J that can be sheltered in place or locked down economically, because the remaining 1 minus L bar J are essential workers. They may be nurses, there may be delivery workers that are needed, or work in the defense industries, or making ventilators, etc. I'm going to assume that the cost of an individual not participating in the economy is his wage WJ. In general, for such a big change, you may want to allow for capital labor substitution. We discussed that, but I'm not going to get into that here. And this is the most important element that I want to emphasize. The effectiveness of a lockdown is imperfect. You can lock down people, but they may still go out of the house. They may still go to parties. They may still be able to transmit for other reasons. And that's going to be captured by eta j. This could be within family or between family. So therefore, fraction of interactions that are reduced and do not transmit infections as a result of the lockdown policy is going to be 1 minus theta j LJT. So if theta j was equal to 1 and LJT was equal to 1, then you reduce infections to 0 for this group. But because effectiveness is imperfect and the lockdown is never going to be equal to 1, L bar J is not going to be equal to 1, or may not be, this will never be 0. Let me also assume that the vaccine is going to arrive at some time t, plus cure is going to arrive at the same time. And then after this point, we can reduce infections to 0. So we do the t stochastic, but here I'm going to assume t is 1.5 years. Okay, that's the model. And here is the summary. It's the same as what I showed you before, except that I've now explained this structure here better. And I gave you the foundations of this equation. So new infections in group J is going to be beta times 1 minus theta j LJ SJ. So that's the factor that you apply because those who are susceptible are locked down. We have this eta K, which reduces infections because the infected themselves are isolated. But you see here, we also have 1 minus theta K LK coming in on the infected side. So this makes a lot of sense, but it's an important observation. Because new infections in the baseline model are quadratic, essentially are the product of SNI, then the lockdown policy is going to have a quadratic effect in reducing infection. And that's going to be the reason why lockdowns are potentially very effective if you can manage them. And then finally, the model, to close it, we have two objectives: lives lost and economic losses. Lives lost, no explanations needed. I'm just summing over the lives lost in the two groups. Economic losses, some explanation, but I'm not going to go through this equation. Economic losses have two sources: those that come from lost production, but also because those who die, who perish, are not going to contribute to future productivity. So we take both of those into account. All right. So let me stop here. I'll go back to this equation in a second and see whether if there are any questions about the model.
Okay. Daryl, there are some questions here. Okay, what's the difference between S1 and S2? I think those are two different groups, right?
Absolutely, yes.
How do you target the lockdown while also taking into account the nature of most, for instance, African economies, which are predominantly informal?
Right. I think that's what I was trying. That's a very important question. I was going to come back to that, but since it is raised, let me comment on it briefly. That's why I said at the beginning that this is calibrated to the US economy. In emerging markets, there are two challenges, or several challenges, but two of them I'll highlight here. One is that the family structure is more complex. So targeting lockdowns is going to be much harder and maybe impossible, or the theta is going to be very different. And second, informal economy is going to make any lockdown more difficult. Of course, on top of it, there are fiscal problems, and coordinating face mask wearing and other things is going to be harder. Vaccines may come later. There are a lot of problems in emerging markets. I will actually, this is relevant, or are there any other questions?
So I was also thinking in terms of life loss that you have just mentioned. And so again, obviously you are assuming the US economy, you have the US economy in mind, but is there any way that you can actually account for differences in skills, or like that we have in South Africa, for instance, this huge inequality in skills that we have here? Yeah,
absolutely. That's very easy to incorporate, and we can talk about that. But obviously, there are other issues when you go to differential lockdown by skill, because actually the people who are most in need of income would be the poorer people. So if you lock them and you don't have social insurance, that's a problem. So, again, the experience of the developed world is different because they had the fiscal capacity to roll out unemployment insurance and social insurance, which is different in the emerging world.
And then there is this question coming from Dambala. What is driving the shape of and the slopes of those curves?
We'll see that. That's going to be that's going to be related to the parameters, but I'll get into that. That's a good question.
And then there is a question from by Don Ross. Can we expand the model reasonably easily to take account of long-term health consequences to those who don't die?
That's a great question. Yes, absolutely. That's very easy to incorporate the model.
Okay. And with reference to the economic loss equation, majority of the lives lost are those above 65 years who already have retired, hence no loss of production due to their absence.
Right. So yeah, we'll see that, and I'll talk about that. Thank you.
Okay. Shall we go ahead then? I think
All right. So let me now give you two qualitative points, and then I'll jump into the calibration, show some results, and then we can open up for discussion. So what does targeting achieve? So the first one is that it's pretty obvious. When you target, you do better tailoring. You raise the lockdown for the old. You can lower the lockdown for the younger groups, not perfectly, because as I said, the two groups interact, but that's going to bring immediate benefits. But the second is a more subtle benefit. And that's particularly relevant for developing world. Because as I said, you'll see that in the qualitative analysis, the quantitative analysis also. There are two different types of solutions. One involves what I'm going to call wait for the vaccine. The other one involves herd immunity. Herd immunity is that enough of the people get the disease before the vaccine that the disease dies by itself. By all accounts, no advanced economy is going for herd immunity. Perhaps with the exception of Sweden, but even then it's not clear. But it is inevitable that many developing countries are going to go for herd immunity because the vaccine is not going to arrive in time. They cannot keep the economy locked down, even in partial lockdown for a year. The fiscal resources are not there. But even herd immunity can benefit greatly from targeting. And the way to see that is with the use of this picture. Imagine we have two groups, old and young. 0-0 is everybody has been infected. 1-1 is nobody has been infected, everybody is susceptible. We start from here and we go down. This green area is the area of herd immunity. You actually never go to 0-0. The moment you enter into this green area, enough people are infected that infection stops spreading, and then it not immediately, but it quickly dies down. So you might think of this model as a dynamical system, as a continuum of steady states. And the green area is the basin of attraction of all of these steady states. If you do no control or uniform control, then you follow this dashed line. Infections and the parameters are the same for the old and the young. Essentially, the ratio of old and young infections and susceptible remains the same. But with control, you can actually enter the herd immunity area from different parts. And the benefit of that is that even as you're achieving herd immunity, you can protect the old so that you achieve the herd immunity with the younger and healthier groups being the ones who are exposed and the older ones suffering less deaths. And I'm going to show you that in the quantitative analysis. And then this figure also clarifies what's the difference between a wait for the vaccine and herd immunity policy. Essentially, these trajectories are giving you the direction, but then there is the question of how fast you are traveling. So imagine there is a uniform control, but it's very tough. So then you go very, very slowly. So when time t comes, you're still in this white area. That's wait for the vaccine. Or you go very, very fast. So by the time t comes, you already entered the green area. That's herd immunity. So those are the two qualitatively different types of policies that we're going to see. All right. Parameters. So since time is short, let me go fast, but these are parameters from the US and the disease parameters from Ferguson et al. That's pretty conventional, although the convention is changing. The most important parameter in some sense is beta, which maps into what epidemiologists call R0, the reproduction rate, the basic reproduction rate. So the initial numbers from China suggested this could be as high as 3. Later it's 2.4, but I think 2.4 is too high, especially once people are aware and they're doing some basic hand washing, social distancing, and face mask wearing. But I'm going to start with 2.4. One implication of this is that number of deaths calibrated here is going to be pretty high. So if this is 1.8, you get many fewer deaths. And then for illustration reasons, I'm going to start with no network structure, or the network structure is uniform, meaning that the old and the young interact in the same way that the old interact within themselves. Again, that would be very relevant for a country where there is family structures, increased interactions between age groups. But I want to do this just for simplicity and transparency first, and I'm going to show you at the end what happens if you do a realistic age-dependent matching rate. Group sizes are to match the US, and here is in the answer to the question about retirement. So we take retirement into account. So as a result, the older group has about a quarter of the income of the younger and the middle-aged group. But you can change those parameters, and I'll show you how to change them. I give you access to a program at the end. Hospital capacity effects is a very contentious area. We do some experiments. Let me not get into that, but we do allow for some sort of convexity, especially the hard constraints I'll come back to later. The US, unfortunately, and same for South Africa, but US is worse. Very low testing and isolation, so that translates into eta j is equal to 0.9. Now, these are very important. We assume theta j is equal to 0.75. So what that means is that, and I think that's not a bad estimate of what's going on in the US, about 1 out of 4 people are disobeying either openly or covertly the lockdowns. They are going and seeing their elderly relatives, they're going to parties, they're not wearing face masks, they're going out, etc. So that's what this means, 0.75, 1 out of 4. And then maximums is that 30% of the young and the middle-aged are in the essential business. Okay. The cost of death, we calibrated from various different sources. Let me not get into that. Vaccine comes in 1.5. All right. So let me show you the results. The red line, so the red curve, is the empirical equivalent of what I showed you at the beginning. Pareto frontier with the present discounted value of economic losses and fatalities as a fraction of adult population. This point here is just one of the points along the frontier. We call this the safety-focused policy. It's not a super nice policy because it still involves a lot of deaths, but it's just a name. It says that we're going to keep adult mortality rate to less than or equal to 0.2% of the population. Now, what I'm going to show you next is, okay, or we can compare this to, say, for example, an economy-focused policy somewhere here, which says we're going to keep the output loss to less than 10%. Okay. I'll explain these numbers in a second. But what I want to do is first show you what are the optimal policies that achieve this. This is where much of the work in the paper goes to, because computing optimal control programs here is not a trivial thing. So that's what part of the methodological contribution here is. And as I said, this is what you can have access to, and I'll give you some references at the end. So here is how the safety-focused uniform optimal policy looks like. You have a fairly quick ramp up in the lockdown. About 50% of the economy is locked down for over a year. When we first wrote this in April, people thought this was pessimistic, but it's actually not that pessimistic, even though I think face masks, etc., have improved the situation. These on the right, you have the infection rates, young, middle, and old. They're all on top of each other by assumption because there is no differential policy and the infection rates is assumed to be the same. And this is the important point here. The reason why this infection rate picks up at the end is because there is no herd immunity. See, once you know that the vaccine is coming, you start relaxing the lockdown. And the reason why you're starting to relax the lockdown is you say, well, I'm not worried about this exponential growth anymore because before the exponential growth comes, cure and vaccine will be implemented. But then what that does is that the infection rate starts peaking up. You get a peak as large as the initial peak here. But you immediately nip it in the bud because of the vaccine. Now, notably, and that's that this table here gives you, the economic costs of this are very large. So it's about a present discounted value of about 37%, sorry. Now, 37% of 1 year's GDP, let me try to explain what that number means. That's the total cost of the pandemic, which lasts 1.5 years, as a fraction of 1 year's GDP. So what that means, actually, when you unpack it, is that about 7% of it or so comes from excess deaths whose productivity contributions to the future have been lost. And the remaining 30% means that you have about a 20% GDP loss every year because of the strict lockdowns and everything. So that's a pretty grim picture. You have a 0.2% adult mortality and and still a very severe recession. What if you were a little more relaxed about deaths and you went for the economy-focused policy? That's the bottom here. Now the lockdown, again, there is a lockdown because you want to slow down the disease. This is the flattening the curve. But it's much less severe. It peaks at 35% of the economy, and it comes to an end in 200 days. Again, this is not, even when you are economy focused, it's not an immediate end to the lockdown. Never, nowhere you get Jair Bolsonaro or Donald Trump. And this is very costly. You get a very, very large peak of infections. As a result, you keep the economic loss to 10% of GDP overall a year and a half. But you have much higher adult mortality, almost 1%, slightly over 1%. But in this case, you see that you have herd immunity. How do you see you have herd immunity? Well, you see at the end, even though there is no lockdown, infections are coming down. That's a telltale sign of herd immunity. And you can look at it, actual infection dynamics more closely and the R0 dynamics, but I'm not going to show them because of shortage of time. Oh, actually, I showed them here, but I'm going to skip them. All right, here's the bottom line. If you instead engage in targeted policy, you have massive improvements. So in this, on the left, the green curve, sorry, the green curve, yes, that's right, is what you can get with semi-targeted policy, just applying a differential lockdown on the older group. And if you allow that, you see that the Pareto frontier shifts in substantially. And then you see what the lockdown policy that is going to bring that is here. You apply perfect lockdown for the full year and a half on the older group, and a somewhat faster rollout of the lockdown on the younger group. As a result, you have 1/3 less economic costs. But notice, again, this is waiting for the vaccine. So this is the shift from this point here to this point here. If you are going for the economy-focused policy, the gains are even larger. Now, you can have an even shorter lockdown, and you can even let the older group out a little bit before the vaccine comes in about 1 year and 3 months. And the fatality rate has been reduced to less than 0.5% instead of more than 1% as a result of the uniform policy. Overall, wherever you want to be, this big shift here. This is with the semi-targeted policy. Semi-targeted policy is attractive because, as I said, one of the challenges of targeted policies is the difficulty of implementing. You see here that it's actually very easy to implement. It's just the economically less active and easily identified group is subject to a more protective lockdown policy in order to reduce their infection. Now, we do a lot of other things, but I'm going to, since time is short, let me emphasize a few things. The first one is that you could look easily at the full targeting policy. Now you treat the middle-aged and the young differently also, and that gives you the blue line. But the blue line and the green line are indistinguishable because the benefits of full targeting is very small. They're not identical, you do treat them differently, but the benefits are very small. Understanding why actually reveals the logic of what's going on here. The reason why you're locking out the young and the middle-aged isn't because you want to protect them. It's always in order to protect the more vulnerable group, the elderly. You're worried that the middle-aged and the young are going to carry the virus to the elderly. But once that's the objective, whether you lock down the middle-aged or the young doesn't matter so much. You just want to lock everybody else who's going back to work so that they don't go back to work and mingle too much. So that's the reason why semi-targeting and targeting are very similar. And that's a very important insight, and that's what simplifies the targeting policies. You can do a lot of other things. You can keep mortality at a lower rate so that you have even more severe lockdowns. That way you can reduce mortality to 0.05% with more economic costs. You can worry here about, this was the question that was asked, whether you're treating the elderly differentially because they are already retired or because they're more susceptible to the virus. It's all because they're more susceptible to the virus. And we show that by splitting the elderly into two groups, elderly retired and elderly working. And you want to treat the elderly retired and the elderly working essentially identically because they're both very susceptible to the virus. One has a higher opportunity cost. It doesn't matter. You want to have both of them isolated because, again, this sounds very severe when I say it like that. I mean, you do it in a way that doesn't fully isolate them socially, etc., but you protect them to the same degree. Let me point out two other things, and then one more robustness check, and then I will conclude. This framework becomes particularly powerful once you recognize that some of the policies that you can adopt create what we call group distancing. What that means is that you can try to reduce the interactions between groups. For example, if you say that nursing homes, where half of the deaths in the United States, Sweden, and the UK have been, cannot be visited during the pandemic by younger individuals, or they have to be visited only after some COVID tests have been taken, that would be a group distancing. You're preventing the infection from going from the younger group to the older group. Since the logic of the lockdown policy, as I've just explained, is to do that, to slow down that transmission, group distancing is very useful. So here I analyze group distancing and show you that with group distancing, you can get much, much better outcomes. Same with testing and tracing. If you combine testing and tracing and group distancing, you can get much, much better outcomes. There are a lot of issues here that you can study. Like, for example, what happens if you change the arrival date of the vaccine. And we do a huge number of robustness checks. Let me mention only two of them. One of them is something that's very popular in the epidemiology literature, which is to impose a hard constraint. They impose a hard constraint, which means that infections cannot exceed a certain amount, because that would be the ICU capacity. But then this motivates some of the epidemiology literature to say, well, a second wave is inevitable. That creates the impression that a second wave, as the one that we are experiencing right now, is almost optimal. And that's so mistaken, and that's why we do the hard constraint version. And here is the optimal policy with hard constraint. To remain on the constraint, you may indeed have a slight non-monotonicity, but you never, in an optimal policy, have a second wave. So I would say that a second wave is a telltale sign of massive policy mistakes by our government. All right, a bunch of other things. Let me do the final thing, which is, here we use the data from the BBC Pandemic Project and allow for different age interaction rates between different groups. The overall conclusion that there is a robust shift between targeting and uniform policies remains. But now when the old interact more with the old, this gives you more options. So now the optimal lockdown policy can start letting out the elderly to go out, consume, and even perhaps some work, because their interaction with the young group is lower, and especially once the young group's infection rates are falling, that's enough protection. So there's much more room for doing things. Again, some of these are very US specific because it depends, or Europe specific. This sort of interaction structure, this is not gonna fit South Africa, it's not gonna fit Nigeria, but the tools are available. And then the final thing, we have an interactive dashboard, which is at this email, at this website. You can go and enter the numbers that you want, and you can get the Pareto frontiers and the optimal policies. And we also have the programs fully worked out, so we can, those who want to go deep into this, you should write to us, and we can guide you towards how to do the optimal control. Thank you. I'll stop here and take some questions. And I'm going to leave this for a few more minutes before I stop sharing, so that anyone who wants to get the address of this website can do so. Thank you.
Thank you, Daron. There are some questions here. I'll read them for you. Is there uncertainty of any sort around veracity of herd immunity? That is to say, whether it exists for this novel virus?
Yes, there's a huge amount of uncertainty, and we haven't dealt with that. So that's a great question. A really ambitious project would be to do robust stochastic optimal control in this framework, but of course that would be very hard, so we haven't done it. But obviously that's in terms of the modeling and theoretical contributions, that's the next level. So you recognize the uncertainty, you even recognize that some of that is unknowable uncertainty at the moment, but we haven't done that.
Then there is another question here, from Diana. What happens to the overall outcome of the model when we interact herd immunity and long-term consequences of the disease?
Great question. So as the earlier question from one of your participants noted, there are no long-term consequences here. And that makes herd immunity relatively attractive. So it's not saying that herd immunity is optimal. So one of the reasons why I'm giving you the Pareto frontiers is because we don't want to be in the business of saying this is the right trade-off, etc. I think every individual, every country, every government, every political party will have a different trade-off. But that trade-off and the shape of the curves, etc., will depend on what are the costs of herd immunity. Here, the costs of herd immunity are major. You only get to herd immunity if you have enough infections, which means a lot of deaths. But there might be other costs, exactly like what Diana is saying, that those who are infected may suffer long-term consequences. We just don't know. We don't have enough information on that. There are conflicting papers on that in the epidemiology literature. There's certainly some people who will suffer long-term consequences, but how common it is, it's not known.
Then there is a question that I missed in the first round. In some SIRD models, we observe time-varying reproduction rates. How do you think about that in your setup?
Yeah, the reproduction rate is time varying. Sorry, I should have made that clear. In fact, let me show you that since I have not stopped sharing my screen yet. So here is the reproduction rate of the disease under the optimal uniform policy and under the optimal uniform policy in the two cases of safety focus and economy focus. So it's highest at the beginning and then it declines. Actually, if you didn't do control, it would increase. Oh no, it wouldn't increase. Sorry, it always declines. But when often people refer to it, it's a little bit uncertain. They refer to R0. R0 is really the value of that reproduction rate here. But then when we are in, say August 2020, they might refer to R0 at this point. So it's a little confusing.
And then Daron, there is a question from Alan Polo. Is herd immunity an appealing objective if antibodies are short-lived?
No, again, that's a very, very important point. I said that, but I said it in passing. Thank you for bringing it up. The assumption here, as in the standard SIR models, and that seems to fit other viruses, given the immunology information that we have, is that antibodies are forever. So you get immunity. So in the case of COVID-19, we don't know. Some people believe it is forever. Some people believe it's short-lived and maybe for a year or so. So if it's a year or so, then it's a tricky question because herd immunity actually kills the virus. The virus disappears. So you don't need immunity to last for 50 years. But whether a year is long enough for the virus to completely disappear or it would come back, that's a very complex question. So we didn't get into that.
Okay, and let me see here. There are more questions here. Let me just find them. Okay, here it is. Okay. Do you think hard lockdown is a necessary step to enforce differential behavioral changes, such as the young not going to see the old and things like that?
That's a question we don't get into. So once you determine this lockdown, there are many ways of implementing it, but some of them may or may not be feasible, and it would depend on institutions, norms, and other things in countries. So a lot of this could be achieved by voluntary behavior. That's what Sweden tried to do in some mixed way, for example. But the evidence is that most of the people in most countries are definitely not taking into account the external effects they create on others, even within their family, even within their broader family. So yes, I think some institutional regulatory limits are necessary. I think I'm seeing very well-educated people still willing to go and visit their elderly relatives in nursing homes, even though they should know that there's a very high risk, not just to their relatives, but to everybody in that nursing home. So I think such things, and you see what's going on in the US and parts of Europe, where as soon as the lockdowns are lifted, parties start, I think suggests that doing this purely via voluntary social distancing is difficult.
And just to provoke you a little bit on the institutional side, is it easier to implement such a lockdown in less democratic societies? I know your model doesn't account for that, but out of curiosity.
Well, that's something actually I'm working on right now in China. So you can never do everything by fiat, like top down. But you know, the interesting thing is that many authoritarian countries are also able to generate what Timur Kuran called preference falsification. So people accept the value of authoritarianism, or they don't express their views. They grow to trust the authoritarian governments even when they are incompetent. So there is evidence that people who trust the Chinese government were better at adapting to the lockdown, even though there are reasons that it's a little naive to trust the Communist Party in China. So this is a more complex period, but that doesn't apply to perhaps less competent authoritarian government. I don't know. Those are questions that you have to investigate. But I'm trying to do one sliver of that.
And then there is a question here from Eleni. What will happen to the outcome if a risk-based lockdown is introduced, and how it will interact with slow development of herd immunity?
So I think age-based policies or group-based policies can help the right type of herd immunity to develop. So this is the point I was trying to make here. This is a non-obvious point. But even if you're going to go for herd immunity, you can do much better, especially in terms of mortality, if you do some amount of targeting. So even in the developing world where targeting is hard and you may be forced to go for herd immunity, we should at least consider targeting whether it's feasible and how beneficial it will be.
I see. And perhaps one last question from Nicola. Curiosity, retirement homes were a strong vehicle of spreading disease and mortality. How isolated should old people be for the effect of isolation to be a reduction in mortality?
That's a great question. That's a fantastic question. So it's clear that, and you know, this actually is a partial answer to the earlier question as well. If you ask the elderly, they don't want to be isolated. And the reason for that is threefold. One is that they are underestimating the risks. I don't want to deny that there are behavioral. Second, they are clearly not taking into account the external effects. Once they get it, other people are going to die as well. But third, and that's very important, they see lockdown as complete isolation. which is socially very costly for them in the last, stretch of their lives. So if you're going to do this, it has to be combined with other measures in order to improve social health and psychology of the elderly. So we'll find ways of them to communicate with their families, create enough of a social environment so that the cure is not worse than the disease for them. So obviously, and then we've actually has the other sort of short paper that goes through some options for that.
Okay. Let me just ask the participants any other question, folks, either by writing, or would you like to ask a question directly to Darren? 1, 2, 3.
This is I looked at the participants, and I don't think they are allowed. Otherwise, I would have also encouraged them to directly ask. But I think because this is being run as a webinar, they don't have the ability to ask them directly, unfortunately.
Okay, let me say thanks to Darren Acemoglu again for availing himself and talking to us here. I think it's great. Also, let me say thanks to ERSA for making this webinar series a reality down here in South Africa. And just one more thing, the working paper is, it became a ERSA working paper, so it is available from our website and it's indexed on RePack. And I've been recording also this webinar, and it's going to be available from ERSA's YouTube channel. So thanks again, and I'm stopping recording this now.